Okay, this is gone. So in the 6th week, we're going to talk about the linear independence. Okay, linear independence of vectors. We're going to talk about the basis. Okay. Then we're going to talk about the coordinates. And then after these topics, this will not be the topic of today, but we'll cover also the linear transformations. Okay. Linear transformations. Now, the relevance of all of these topics that we're going to discuss, they are related that initially we have to understand what is a linear independent set of vectors, what they do. And the moment that we understand how linearly independent vectors, how they can serve as a basis for a specific vector space, after we learn this, we learn how we can define the coordinates in different bases. Because a plane, we can describe or we can span a plane using an infinite number of bases. So we can select any one. Some bases are better than the others in terms of practical applications. And this one, in a couple of weeks, very soon, we're going to understand more in detail what I mean with this. What I mean with trying to find a basis that does a better representation of the data that we have in hand. So after the basis, we're going to talk today for coordinates. Next week, or in a couple of sessions later, we're going to talk about the linear transformations, which enable us to pass from one basis representation to another, okay? Because it is often when the data set or when any other array of numbers is provided to us, we can always apply these linear transformations to represent it in a more, in an easier way. Now, let's continue with the, okay, wait a second. So here we have a couple of examples. And initially, let's start with the following. So let's give first, initially, the definition of linear independence. If V1 up to Vk is a set of vectors, if this is a set of vectors, then the vector equation alpha 1 V1 plus alpha 2 V2 plus alpha k Vk is equal to 0. This is equal to 0. This one has the trivial solution so this is our equation, and we know that whenever we talk about a specific equation, we have the vectors which is given, and in this equation the unknown will be these coefficients. So we have to find alpha 1, alpha 2, up to alpha k. And when we try to determine this means that the unknown is the following. So when we say the trivial solution, or let's give this the trivial solution is the only solution. The trivial solution is the only solution that then V1, V2, Vk are linearly independent. Okay? So apparently we had a system which in fact this looks like a homogeneous system of linear equations. Why is this homogeneous? Because linear equations traditionally we write them as Ax is equal to B, When b is equal to 0, this becomes ax is equal to 0. Now, the x in this case is not x, but let's denote this one as a vector alpha. Okay, let's try to do this a little better. So this is a alpha, this is equal to b, but this is a special case when b is equal to 0. And having a trivial solution, this means that the vector alpha, this is equal to alpha 1, alpha 2, alpha 3, and all of these, they look like this. Or we can denote this one as 3 by 1, 0 vector, which is 3 by 1. If this is the only solution here, which means that we can linearly combine all these vectors, and this is equal to 0, only when all of these constants are 0, then we call these independent. So these are called linearly independent. Let's give a couple of examples, a few examples. So here we have 1, 0, 0, 1. The question that we can start with is, are these linearly independent or dependent? What do you think?
They are linearly independent.
Independent.
Okay, this means that actually, let's try to pose this one in the traditional form, which is the following. If we do a constant C1 times 1, 0, plus a constant C2, which is 0, 1, for which values of C1 and C2, this is equal to 0.
Only for 0.
Zero.
That's correct. This is the case only when C1 is equal to C2 is equal to 0. So the solution vector is the 0 vector. That's good. Then immediately we can say that these two, they are linearly independent. Okay. And then what about this other vector, 1, 1, minus 1, minus 1? This pair of vectors, is this linearly dependent or independent?
They're linearly dependent.
Dependent.
Start with the D. Is it dependent or independent?
Dependent.
Aryan, okay, Aryan is saying dependent.
Dependent.
Okay. So these are dependent pair of vectors, because here we can say for C1, C2, it is equal to 1, 1, which means that C1 is equal to 1 and C2 is equal to 1. This means that the C vector is different from the 0 vector. This implies that the vectors, they are linearly dependent. Okay, so these are linearly dependent. What about, let's give another example here. Let's assume we have AB, which is a vector, CD, okay, and these vectors. Let me ask, wait a second. Let me ask someone from the class. Anyone is a volunteer, you can raise your hand. I have a couple of questions. Terence, okay, so we have Terence here. Wait a second. Terence, what are these two vectors? They belong to which subset?
R square.
That's good. So these two, they both belong to R square. That's good. Now, assume that we have a third vector, which is FE or EF, whatever. Now, the question is, these three vectors, are they linearly dependent or independent?
We are linearly dependent.
Why?
Because on an Rn space, we can only have n vectors that are linearly independent, not more.
That's correct.
So in R2, we only have two vectors that can be linearly independent from each other.
That's good. So in R square, we have two vectors which can span a plane. Let me call this a plane, okay? A plane is two-dimensional. So this means that this implies that any vector B can be described
as a linear combination of the two other vectors in R2.
Okay, that's exact. Of two other vectors. But now, let me ask you this one, Terence, vectors. Do you have any constraint for these vectors A, B, C, and D?
One of them should be different from 0 vector.
Okay, one of them should be different from 0 vector, but anything else? So if we construct, sorry, this is AB, and here we have CD. So if you see this pair of numbers like this, can you add any other constraint?
The two vectors should be different from each other too.
The two vectors should be what?
Different from each other.
Different from
Not
each
the
other.
same. Not the same vector.
Okay. Anything else? What can you say
They should
about
not be expressed as multiple
Also, the
of
two
each other.
vectors shouldn't be linearly dependent with themselves.
That's good. So AB should be linearly independent of vectors CD. Okay, and how can we check this linearly independence of two vectors? The easiest way, what can you say about the determinant of this matrix 2 by 2?
The determinant is AD minus CB, and the two vectors.
So AD minus CB, this
should
one,
be different from 0.
that's correct, okay. So this should be different from 0. Okay. Let me figure out one little detail here, which is solved. Okay, let's go.
Can you tilt the camera to the right a little?
You don't see the rest, right? Okay.
Thank you.
Okay, you are welcome. Okay, so it looks like we can produce vectors which are linearly dependent or independent. And in fact, at this part, we can also write a conclusion. So we can say that two vectors are linearly dependent if they are scalar multiples of each other, of one another. Which means the following. So if we have a vector which is, let's say, 2 minus 1, can you produce, let me ask Terence again, so can you tell me a vector which is linearly dependent to this?
Dependent?
Yes, dependent.
Minus 4, 2.
Minus 4, 2. That's true, because this is equal to
Minus 2 times 2 minus 1.
2 minus 1. Okay, let me have another volunteer here. You can raise your hand. We have 2. Elio, let me start alphabetically. I thank you. We have Elio here.
Yes.
Elio, can you tell me another vector which is linearly independent with respect to this?
Dependent or independent?
Independent.
3 minus 1.
3 minus 1, okay. So how can we check this one? We can check the following. Is this, with a question mark, equal to a constant C?
C times R vector.
So this is a question, okay, we have to think about this one. So we can check 3 is equal to 2C, and then we have minus 1 is equal to minus C. So from here, we get the C is equal to 1.5, and from here, C is equal to 1. So it looks like these are not satisfied. What about this one, Elio? What do you think, Elio, if we have a number here, 2 minus 1, and this would be, let me say, and you want to produce a linearly dependent vector, which looks like this, minus 8a. These are
we multiply by minus 4. It would be minus 8, 4.
That's correct. We have minus 8 and 4. Okay, that's fine. So these are all linearly dependent. And what if you want to make another vector which is linearly independent of this, but you keep this A the same?
Now it should be independent.
And now it should be independent, yes.
We just change the 4, we make it, for example, 5.
That's correct. So we can do this. So this is dependent, and here we have this would be independent. Let's go. Okay.
Yes.
You just change one of them, and you do a fine job. Now we can also easily notice that we have a pair of vectors which are linearly dependent. This would have the determinant of this matrix would be equal to what? What is the determinant here?
0.
0.
That's correct. We get 0. Okay. So apparently, if we have a set of vectors and we want to check whether they are dependent or independent, a fast technique to check that is to find out about the determinant of the matrix. Now, whenever we analyze the linearly dependence or independence of vectors, it is this concept, it's equivalent to the linearly dependence or independence of functions. Okay? So we can assume for a moment to have a look at the equivalence with functions. So with vectors, it is intuitive to say that if one vector is the scalar multiple with another one, they are dependent. But let's have a look here, example 1. Let's assume we have f1 is equal to x and f2 is equal to 3x. These two functions, are they dependent or independent?
Linearly dependent.
They are dependent.
So,
Dependent.
2, they are linearly dependent for 2 reasons. The first reason can be that the ratio between f2 and f1, so we can say here f2 over f1, this is equal to 3x over x, this is equal to 3. So they are scalar multiples of each other. And the second reason, which is in principle is the same reason actually, but we can construct a coefficient matrix which would be C, which this one is equal to, let me think for a moment, this can be 3 minus 1, right? So a solution 3 minus 1 proves that C1 times F1 plus C2 times F2, this is 0, right? I believe this is clear because we do 3x minus 3x, we get 0. And in this case, since C is equal to this number, this is different from 0, then we immediately say that these are dependent. Now, let's see a second example, again with functions. Assume that we have a function f3 of x, which is equal to x, and f4 of x, this is equal to x squared. Are these two functions dependent or independent?
Independent.
Independent.
They are independent. Why? Because we have c3x plus c4x squared. When is this equal to 0? This is equal to 0 only when c3 is equal to c4 is equal to 0, which we can simply say that c3, c4 is equal to 0, 0. Or we can even reply it like this. Now, similarly to this, we can have a third case where f5 is equal to sine x and f6, this is equal to x cubed. What happens for f5 for x equal to 0?
It becomes
It's equal to 0.
That's true. What about f6 when x is equal to 0?
It's
Still
0.
equal to 0.
0.
0. Are these two functions dependent or independent? Cleo, let's pick Cleo. Cleo, can you answer this?
I don't know.
Let's think about this one. So, if we use the same idea as we followed in here,
No, making the x equal to 0 doesn't mean doesn't say anything.
so it's not conclusive, maybe you want to say.
That's not conclusive.
Okay, but in general, what can you say?
Well, we have to follow the method c3 times sine x plus
Okay.
c5 times sine x plus c6 times x cubed.
Yes. When is this equal to 0?
When
When
both
both
c5 and c6 are equal to 0.
That's true. Okay, so this one also is true only when C5 is equal to 6.
Equal to c6 is equal to 0, which means that we have the trivial solution and the functions are independent.
That's true. Linearly independent. Okay. So some students, including myself, might argue that the principles, or when we see the linearly dependence or independence of functions, this might help us to get a better understanding of linearly dependence and independence in general. So examples of this one, let me give you another exercise. So let's say ei0 e to the power j beta 1 x plus e r0 j beta 1 x is equal to et0 e to the power j beta 2 x. So we have an equation here, and the question is, now we are looking at the problem from a different perspective. We just want these somehow to be linearly dependent. But for what values of x? We put no constraint on the values of x. And then, since these are exponentials, and you are going to be computer engineers, and the computer, sorry, I forgot the exponential term here. And the computer engineers, they are afraid when they look at an exponentially increasing or exponentially decreasing term. So they change it so fast, and in order to have this equality, always valid, what we should have is that these terms should be equal to each other. Then we can say that the exponential of this is equal to this and this. So we can say b1x, this is equal to b1x, actually they are on the same side. This is also to b2 beta 2x. So we get an equation here. Then, if you cancel all of these like this, we can also conclude the following, that ei0 plus er0, this is equal to et0, okay? So this is all that we can conclude easily from the good understanding that we have regarding the linearly dependence or independence of the functions. Let's see. Okay. We can provide here a specific definition which includes the following. Any set of n vectors in Rn must be linearly dependent if what? N larger than m or n smaller than m. What do you think?
If n is smaller than m.
So you are taking this one.
Yes.
Let's think about this one for a moment. Would everybody in the class agree with this?
Yes, I agree with him.
Yes.
Larger than m. So let's see before a while, before a few minutes, we wrote three vectors which were part of the R2. So we wrote here AP, right? We wrote also
FP.
and FE. And we said that we have three vectors, right? So here n is equal to 3. For this specific case, all of these, they are members of R squared, okay? So here we have m is equal to 2, okay? And then someone from the class correctly reported that these are linearly dependent. Why? Because we have 3 vectors in 2-dimensional space. So these are linearly dependent, and this is happening because what? Because we have this, right? So probably this is going to be like this. You can think about this one for a moment, but to many us in the class, this might look like a more correct answer. Would you agree with this?
No.
Okay. So we have to think about, but would you agree with this case? So A, B, C, D, and F, E, they are members of R squared, right?
Yes.
Now, if we have 3 vectors, which means n is 3, are these linearly dependent or independent?
They are linearly dependent.
Dependent.
Okay. So if they are linearly dependent, they are linearly dependent because n is larger than 2 or n is smaller than 2?
Because n is larger than 2.
So would you agree that this is the correct answer?
Yes.
Okay.
Yes.
Okay, so you can think a little more on your own, but I believe this is the correct version.
Sir, may I ask a question?
Sure.
In the examples we took with functions, didn't we say because the functions are all part of R1?
Yes, yes.
They are all dependent.
Say it again.
All the functions we mentioned had only x, therefore all the functions are part of R1.
Yes.
Therefore, every function is dependent.
No, they are not dependent because
No, I mean in the examples we took.
okay, these are not vectors. This is a very good question. But the traditional definition or the more formal definition is what I'm going to write down on the board. So this is one function, and this is another function. Okay, and then it is true they are both elements of R. You are correct. But then the definition is this: can we find C1 e to the power x plus C2 times tangent x equal to 0? For which values of C1 and C2 is this identity true for all values of x? So you are right. We have here, but this is not a vector. Okay, here we have two vectors. Now these 2 functions in R1. So let's try to be. So we have apparently our n is 2, and m is 1. This is a good question. So this doesn't match. But here we are talking about vectors, okay? And in vectors, we can. So let's think about this one in this way. If the space is 1-dimensional, we need only 1 vector. That's enough. If the space is 2-dimensional, we need 2 vectors. That's enough. But now, what is the dimension of the functions? So think about this one. For
Functions
sure.
are not constants, not always.
Okay, let me ask you this. What is the dimension of function space?
Size of R?
No, that's too much. That's infinity. But let's think of, well, now this is, what does this mean? We can define this in several ways, but you're going to see this problem at least in the 2nd or the 3rd year. But it is good to construct or to base your reasoning when you go to the 3rd year using what we learned in the 1st year. Okay, it's always intuitive, although, and we'll try to do our best job to keep your intuition open or awake. So I'm asking a question: what is the dimension of the function space, which can be defined as?
Wouldn't it be R squared, Professor?
Well, not really, because these are not vectors. Okay.
And
So
we're in a single plane.
say it again.
They form a plane with each other? Probably.
Well, let me do it this way. So this part, this is a question which I'm going to answer to you in 1 minute with 2 sentences. But before we complete this one, which is like a bonus material for this course, who can answer this? For which values of C1 and C2 this identity is true? This identity is true only when C1.
C1 and C2 are equal to 0.
That's true. So this makes these functions linearly independent. Okay.
Professor, I have a question. The tangent function actually has a lot of asymptotes when it reaches a certain point. Does it mean that when the domains are different, they are not dependent?
You said that the tangent has a lot of singularities, and what was it? The rest? Does it mean that what?
Does it mean because the tangent has a lot of asymptotes, it's not linearly dependent?
No, even in a region where they're both defined, even if we exclude the singularities of that function, where the tangent is not defined, because we define the sine with a cosine, even in a region where both are well defined, this identity, it is true only when C1 is equal to C2 is equal to 0. Okay? So this makes them linearly independent. But this is true, this is the formal definition of the linearly independent or independence. So if we just, without forgetting the definition, we can also do the following. C1 times V1 plus C2 V2. These are vectors now. When is this equal to 0? We say if this is 0 only for C1 equal to C2 is equal to 0, we immediately imply that V1 and V2 they are linearly independent. Okay? Linearly independent, sorry. No, independent. These are linearly independent. Yeah, so the language of matrices and of vectors, it puts some more a deeper understanding into space. What I want to say is that this argument about the dimension, it does not work in the function space. Now, one thing that I believe, is this part clear?
Yes.
I believe it should be, okay. But one thing that I can say at this moment regarding this question, we could say that all the functions, they can be described as the linear, as an expansion of sines and cosines, okay? There is something that we are going to learn very soon. There is a material which is like 300 years old information, which is the Fourier transform, or Fourier series expansion, which states that we can write any function as a linear combination of a lot of sinusoidal functions and cosine functions. So from one perspective, what is the dimension of the function space? We can project everything on sines and the cosines. Okay. So this stays for you to think about it when you see more advanced courses in your study program. And there is an equivalence in terms of how we define the basis of the vectors. Now let's move to another topic. So, and let's see an example here. I think it is obvious, but let's assume we have two vectors, 1, 2, and 1 minus 1. And are these linearly dependent or independent?
Independent.
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 These are independent. What if we add a third vector, which is 2 minus 5?
They are linearly dependent.
Yes, this trigger, these are dependent. Because 2, 5, this is equal to, so the vector 2, 5, this is equal to C1 times 1, 2 plus C2 times 1 minus 1, okay? Now, what about 1, 2 and 2 minus 5? Are they linearly dependent or independent? The first one and the third?
They are linearly independent.
independent. And this, if the first one and the third one, they are linearly independent, we can write here 1 minus 1 can be equal to 1, 2 plus C4 times 2 minus 5. So it looks like we can construct a basis made of the first two vectors, or we can construct another basis for the two-dimensional space using 1, 2, and 2 minus 5. So what does this mean in principle? In principle, this means the following. So we can span the two-dimensional space using this vector. These two vectors. What are these two vectors? These two vectors, they correspond to a graphical representation, which is going to look like this. Which is called, the first one is 1, 0. The second one, it is 0, 1, okay? Then, what is another basis? Let's see, so this is the Cartesian coordinate system, where the bases are orthogonal, or when they are 90 degrees with respect to each other. Now, I want a volunteer from the class. Okay, Enkedi. Enkedi. So, Enkedi, I want to ask you, wait a second, okay. So, my question is the following. So, what is the inner product between these two vectors?
0.
0. That's good. How do we find them? We know that the inner product between two vectors, we write something like this, which is equal to the transpose of the first vector, which is 1, 0, times, right, 0, 1.
The other vector.
This is equal to 0. So, if the inner product is 0, what is the projection of the first vector onto the second?
A point.
Say it again?
A point.
I would say 0, but you are right, it's a point, okay? But because there is always a shadow if you project this one here. This is a unique question. I never thought that it would be a point, but it is 0. Projection of 1, 0 onto 0, 1 is a point, or is 0. Okay, so there is no projection because the cosine of 90 degrees, it is defined as 0. But still, your answer is still original and correct. So now, let's see this other basis, 1, 2. Where is this basis 1, 2 here in this coordinate system? This is 1, this is 2. So this constitutes another vector, which is going to look like this. And the other vector is 1 minus 1, which is 1. Minus 1 is here. So here we have the other vector. Now, again, Enkedi, what is the inner product between 1, 2 and 1 minus 1? One, two, it looks like this.
Well, we can both prescribe them as scalar multiples of 1, 0 and 0, 1, and thus the inner product would be again 0.
I don't know. I'm asking, what is the inner product between 1, 2 and 1 minus 1? Well, we can write it down for
minus 1. Just multiply and lose minus 1.
I just want Enkedi to talk right now.
1, 2 times transpose 1 minus 1.
So this is the transpose, which is 1, 2 times 1 minus 1. So what do we get here?
1 times 1.
Yes.
Plus 2 minus.
So what is the answer?
So it's 1 plus minus 2. So
it's minus 1. That's true. Okay, so here we have minus 1. So it looks like the inner product is different from 0. Okay. Which means that these two, the angle between these two, it is not 90 degrees, and we can easily see that. But the projection is a negative number, okay? So if we look here, what is the projection of this one, of this vector, onto so let's see this red line. The projection of this one is going to be this much, but it's in the opposite direction, so it's negative. Also, what is the projection of the larger vector onto
Professor, that's not vector 1, 2. That's vector 0, 2.
Which one is 0, 2?
The one you have. Acho que visa atuar. Tu tinha me tem.
You are right. Yes, yes. Okay, I did. This is wrong. I believe this is correct. But
Yes.
thanks for reminding me. Yes, it should look a little different. So this is 1 unit here, and we go 2 unit up. Yes, you are right. So this would be the basis, which is 1, 2, and 1 minus 1. Okay, so it looks like this is a basis. It is orthogonal. Orthogonal, it means perpendicular. Perpendicular, it means zero projection onto each other. Would you agree? So the projection of one vector onto the other direction is 0. This is orthogonal. Here we have another basis which is non-orthogonal, etc. So you can put a non to all of these arguments here. And we have this other basis which is 1, 2 with a second and 2 minus 5. Where is 2 minus 5? 2 minus 5 is 1, 2, minus 1, minus 2, minus 3, minus 4, minus 5. So we extend down here. We can erase this one because this was just an inner product between two vectors. And we can use some space to clarify. 1, minus 2, minus 3, minus 4, minus 5. We got 2 units this way. And here we have the other basis, which is constructed of this 1, 2, which we can draw this one here. Okay, so here we have the other pair, which traditionally is going to look like this, and a vector which extends way down there. Okay, so it looks like we can construct for the same space. We can construct we can have several bases. Okay, and now with this discussion here, we are constructing the initial understanding of the basis of a specific space, which in this case is the two-dimensional space. Yeah. Let me ask you one final question, and I can ask Katie regarding this one. Minus 2, 1, 3, 2 minus 2, 4, 1 minus 1, 2. So, and Katie, what I have we have here 3 vectors, and my question will be the following. Are these 3 vectors linearly dependent or independent?
Because we're in R3, so it would be linearly independent.
But how do you know that? Because, well, let me think. Let me make up another vector. This is minus 1, 2, 3, 2 minus 2, 4, and another vector that we can construct, it's minus 1, 4, 13. What about these numbers? Are they, so you said about these and you said these are linearly independent?
Yes.
Okay. What about here?
Unless one of the vectors is a scalar multiple of the others.
This one?
Again, depends. They could be linearly independent.
So how can we check it? How can we check this one in a relatively
Well,
fast?
We again do the definition. C1 times vector 1 plus C2 times vector 2 plus C3 times vector 3.
Can we just find the determinant and then say if they are dependent or not?
Yeah, or that, if the determinant is 0.
Would you agree with this, Enke?
Yes, and then we would find if C3 wants to.
So let's find the determinant of this 3x3 matrix here.
That's 0. I found it. It's 0.
Which one is 0? This one?
Yeah, that's the determinant of that is 0.
Okay, so determinant is equal to 0, which means that
They are linearly dependent.
that's true. What about the determinant here? Actually, are you sure it's 0? Can we try this? This is -4.
I did it with a calculator, so it's 0. I did it online.
That's good. So these are dependent. What about this one here?
That's still 0.
Okay,
So apparently they are both
Is it minus
dependent. Say it again.
In the second one, is it -1, 2, 3?
Yes. -1, 2, 3. 2 minus 2, 4. -1, 4, 13. Okay, so that's true. In order to determine as a small approach to find out whether they are linearly dependent or independent, what we can do is that we can immediately calculate the determinant. And if the determinant is 0, that means that when is the determinant 0? Determinant is 0 where a whole row or a whole column is made of zeros. This happens when the columns are linearly dependent with respect to each other. So that, because intuitively, I'd like to approach this problem also intuitively. So it looks like we have a 3x3 matrix, determinant is 0, so let me write it like this. So determinant is equal to 0, and this is possible only when a whole row or column, either one, o senora o setieta, or a whole column is 0. What does this mean? We get a whole row or a whole column 0 only when we don't have an equation at all, right? We say that we have 3 unknowns, we need 3 equations. But sometimes the third equation is not even there. We did this principle when we discussed the reduced row echelon forms. So, okay, you're right. In case the determinant is 0, they are dependent columns. In case the determinant is 0, they are also dependent columns again. But at the same time, we can say that also the rows are linearly dependent. Because we can take the transpose of this matrix, and if we take the transpose, the rows become columns. So we can say both. Here we have dependent columns, and we have at the same time dependent rows. Why is this the case? Because the determinant of matrix A is equal to the determinant of matrix A transpose, right? So you can say either way. The columns are linearly independent, or the rows, it is not that essential. Now that we are doing all of these, we can offer the definition of a basis, and I hope that with the examples that we covered, at least with the last example, we learned that. Yes. Yes.
So couldn't we say that the number of linearly independent matrix vectors in a matrix is equal to the number of rows with leading ones?
Say it again.
Couldn't we say that the number of linearly independent vectors in a matrix is equal to the number of rows with leading ones?
That's true. That is true. The number of leading ones, yes, is equal to the number of what? Of independent
vectors in a matrix.
Independent, say it again?
Linearly independent vectors.
Vectors, okay, vectors. Well, here we have to consider, we're going to do this one a little later in detail, because the number of leading ones, in fact, this defines also
the rank.
Range.
Let me think. Yes, this defines the column space and the range. Yes. we can call that this is equal to the dimension of range, and also this defines the dimension of column space. Okay? Yeah, but we're going to cover this one, I hope, in today's session. So we should, but if you like, we can have a short break, 5 to 10 minutes, if you don't have any, is it okay?
Break will be nice.
Okay, let's have a short break.